That's great. I hope you had a nice break. So the vote for what to do next was to proceed to newer stuff, or stuff I was involved in. So this Khovanov's table homotopy type, I'll say what that's about in a minute. It was, whatever it was constructed in joint work with Lipshitz, who had previously been a graduate student here. And then the version I'll tell you is joint work with Tyler Lawson and Lipshitz. This version was also constructed by Hu, Križ, and Križ. So one of whom was a graduate student here, and another of whom was at the institute at the time. So very local. Great. So what are we going to do? Goal is for each knot diagram. So for a knot diagram K, I'm going to build a CW spectrum. Okay, I'll come back to what that means in a moment. Xj of k, such that 1, if you take its ordinary homology hi reduced of xj of k, this is the Khovanov homology of k, canonically. And if k and k prime represent isotopic knots, so I'll just say isotopic, then xj of k is homotopy equivalent to xj of k prime. So CW spectrum for us is just going to mean this is a formal suspension or desuspension of a CW complex, a cell complex, finite cell complex. So this is formal. Alternatively, you can just think of xj of k as a big dimensional CW complex, so or xj of k is a CW complex well defined up to homotopy equivalence and suspension. So sigma is my notation for suspension. Okay. Caveats. Xj of k is not some intrinsic construction like you take the 17th branched cover and look at maps from it to, I don't know, RP3 and I don't know what. So is not intrinsic. It's going to be built in a combinatorial way, step by step from a knot diagram. So it's built by recipe from a knot diagram. Well, we don't have an intrinsic definition of the Jones polynomial, so we don't have an intrinsic definition of Khovanov homology, so we can't have an intrinsic definition of this, or I would be, I would have explained that intrinsic definition of the Jones polynomial at the beginning. This gives extra structure on Khovanov homology. But what you might think you get from a space, the first extra structure you think of as a cup product, and it doesn't give you a cup product, not a cup product, because as soon as you suspend, the cup product vanishes. So you only get stable operations on cohomology. Only stable operations. C. There's no deformed version known deformed. So this was like the, I've talked about before, the Lie deformation over like z brackets t. So in particular, we use the Lie deformation to get concordance invariance as invariant S. And we can't just run that story, whatever it was, to here, because we just don't know how to do that. Maybe these things exist. I mean, this is all relatively new, and not that many people have thought about it. So maybe one could run that story, and we just haven't figured out how. So the plan today, this is subject to change if there's a request for change, not today's. I'm going to give the construction of this space xj of k. Well, I'm going to give most of the construction, and some part of it I'm going to lie about, and I'll tell you where the lie is. And actually, it's a homework problem to demonstrate that I'm really, definitely, truly lying. And then, OK, that is what it is. Next lecture, so this is lecture 5. Lecture 6, I want to talk about Steenrod squares. At least my plan is to talk about Steenrod squares. So this is classical homotopy theory just for spaces. So that'll be a digression away from the Khovanov stuff. But I didn't want to assume that everybody's seen that, because it's not in a typical first-year algebraic topology course. Lecture 7, OK, I'm going to correct the lies. So give some more details that I skipped today. And then I want to talk about, at least sketch how you compute the first of these, the first interesting one, on Khovanov homology. Because that's enough to demonstrate that this actually has interesting information to get some very modest applications. And then lecture 8, we'll talk about refinements of the S invariant of S. And actually, the strategy there works not just for this space, but for various other variants on Khovanov homology, so it's also sort of interesting. And lecture 8, as I imagine it, could be done in 25 minutes, so if we run a little over, the earlier ones were OK. So that's my current plan. But it's, if you have other requests, of course, let me know. Thanks to the many of you who filled out the survey. Lecture 6 is not next week, so this is a little bit confusing. These are not the Minerva lectures. These are lectures by the Minerva visitor for the year. But the Minerva lectures for the year are this week, Wednesday and Friday, by Joshua Zell, and then next week, Monday and Wednesday, by Hong Wang. Not here. They're in a bigger room. They're not on this topic. They're about analysis. They're talking about the Kakeya problem. I had nothing to do with organizing them, but I'm really excited that they're happening while I'm here, because I remember learning about the Kakeya problem in this room 25 years ago from Eli Stein. So I'm excited. You all should go to those. Those are going to be much better than these lectures. OK, questions about where we are, where we're going? Everybody strapped in? So we're going to start with a recall. So I'm going to continue propagating my favorite example. Those I'll come. I mean, I'm just saving myself some writing in a few minutes. So we'll come to those boards in a sec. Well, I guess I'm going to be talking about that board in a moment. So I top board. So recall, how do we get Khovanov homology? We start with a knot diagram. That gives us a cube of resolution. So for this one, it looked like this, this, and this. OK. And then from this, we had this Frobenius algebra A, and we took circles replaced by copies of A, disjoint union by tensor products. This was A tensor A, A tensor A, A tensor A tensor A. And this was like the multiplication, and that was the co-multiplication. And then we took the total complex, and the total complex of this, after some grading shift, was the Khovanov complex of K. Great. What are these? So this, for example, is, so what was A? A was Z adjoint X mod X squared. So this A is the free abelian group generated by sort of 1 and X. You can label this circle 1 or this circle X. And this was the free abelian group generated by 1 tensor 1, 1 tensor X, X tensor 1, or X tensor X. You can label this 1 and that 1, or this X and that 1, or whatever. OK. So I want to slightly reinterpret this. So let's let 2 be the category with 2 objects. One is called 0 and one is called 1, and morphism from 1 to 0. So this diagram here, maybe I'll use some colors. This diagram here is a map from 2 squared to abelian groups, free abelian groups. It's a functor from 2 squared. 2 squared is just a category that looks like this. And of course, there's one arrow that way also, to abelian groups. So what I'm going to do is I'm going to instead, so this we turned into that, turned to this. Instead, I'm going to turn this into a functor from 2 to the n. N is 2 this case, so 2 to the n, to some other category B. So this is a new thing that I haven't defined yet. I'm going to then turn that into a functor from 2 to the n to spectra. Think spaces. And finally, I'm going to take some sort of total complex or iterated mapping cone and produce a space, X of K. OK, so there are a bunch of things I need to tell you here. I need to tell you what B is. I need to tell you how I produce this thing. I need to tell you how I do this arrow, so how I go from, I should box the arrow, right? I need to tell you that arrow. I need to tell you this arrow. I need to tell you that arrow. Okay, so that's all. That's what's coming up. I want to tell you what B is. I want to tell you what, in order, what order am I going to do it? I think this arrow, and then this arrow, and then this arrow. At each stage, there's sort of a forgetful map. So you can take a map to the Burnside category, and you can forget to having a cube. This way, this is just taking the cellular chain complex. So once I have this map from the cube to spectra, taking its cellular chain complex is going to recover this. And here, again, taking the cellular chain complex is going to recover the Khovanov complex from this space. Okay, so at each stage, the old construction is obtained by forgetting some information with a new construction. OK. Questions about the plan? Great. These boards. maybe I'll give away a little bit of punchline for later. If I'm just interested in the vertices, what do I have here? At this vertex, I've got z plus z. Right? There's z generated by 1 and z generated by x. Everybody agrees? Z squared, z plus z, same thing. Okay, hard mathematics. And what that's going to turn into, the space element version, is just going to be like the sphere wedge the sphere. So you can think of that as like Sn wedge Sn, some other n. Okay. And this, I have z to the fourth, that's going to turn into the sphere wedge the sphere wedge the sphere wedge the sphere. The interesting thing is, how do the maps show up? Like, what happens with the maps? But I've now told you what's going to be at the vertices of this cube. And then this iterated mapping cone is pretty easy. We're going to do that in one board and some exercise. Okay. So let's think back a little bit more about finitely generated free abelian groups. Redux. So I want to think about free abelian groups. That was what we had at this stage of the construction. Free abelian groups slightly differently. So let's consider a category where the objects are finite sets. Okay, that's not how you think of an abelian group. The object is supposed to be abelian groups, but just think the direct sum over S and S of Z, or like Z to the S. And what's a map between free abelian groups? It's just a matrix. So hom from S to T is a set of T by S matrices of integers. So maybe I'll call my matrix ATS, where T is in T and S is in S. Let's put S first. S is in S and T is in T. And you know, the m by n by m thing with matrices is always confusing. I'm writing it in the correct order, but don't get too distracted by like S by T, T by S. So for example, the set of 1, 2 is an object of this category, abelian groups, free abelian groups. So that's like Z sub A plus Z sub 1 plus Z sub 2, like Z plus Z. And if I looked at, say, hom from 1, 2 to 3, 4, 5, contains, for example, the 3, 4, 5 by 1, 2 matrix, I don't know, 2.271828, I mean, whatever. Okay. And that defines a map from Z squared to Z cubed. Just by matrix multiplication. So it's the right sort of object. So it's the same category again, just these are abelian groups with a basis. Okay. So B, this stands for the Burnside category of the trivial group. You don't need to know that, but that's where the B came from. Its objects are again going to be finite sets. So just the same as before. Hom from S to T is going to be the set of T by S matrices of finite sets. Okay. P by S matrix defined set. So, for example, if I had here is an element of Hom in the Burnside category from 1, 2 to 3, 4, 5. This contains the matrix, I don't know, set of A, B, C, empty set, D, empty set, E, F. There could be more than 2 elements. I'm just going to multiply them and things are going to get more complicated. If I make it too big, my arithmetic's going to become complicated. But it's a matrix of sets. Now you want to know how you compose them, right? That's what you want to know. So given, let's say, the matrix A, T, S in Hom of ST, and B ut in Hom of TU, I can compose these. How? BUT circle ATS is the matrix, I don't know, let's call it something. The matrix CUS, where CUS is the union over T of BUT times ATS. Okay, I can do that. Let's do an example. So maybe I'll start up here. So here's an element in Hom from 3, 4, 5 to 6. This contains the matrix MN P Q. It's a matrix of finite sets. Again, everything I'm taking everything to have no more than 2 elements just to make my life easier when I multiply them, so I don't get too big. So, but I could have more things. So then, if I take, so let's call this matrix A and this matrix B. So then, BA, you just multiply MN P Q times AB, D, empty set, C, empty set, EF. I'm capable of this. This is the set AM. Sorry, let's do it in the right order. MA, NB, sorry, MB, NA, NB. Not done yet. So that was the product of these plus the product of these, so that's PC. This is the first entry. I'm giving you a 1 by 3 matrix. This is the first entry in my 1 by 2 matrix. The first entry in my 1 by 2 matrix. And then the other one, the next entry, I didn't leave myself enough space, is MD, ND, MD, ND, empty set, QE, QF. end of matrix. Okay, so it is a 1 by 2 matrix. That's the right size for this product. And use multiply and add. So it's just like ordinary matrix multiplication, except instead of, for sets, what do you need to multiply matrices? You need to be able to add numbers. You need to be able to multiply numbers. You can add sets. That's the disjoint union. You can multiply sets. That's the product. And so I use product for multiplication, disjoint union for addition. Awesome. But there's more structure here. So given, let's call them something else. Let's say D and E in Hom. Let's do it this way. Given a matrix D, S, T, and a matrix E, S, T in Hom from S to T, it makes sense to talk about a map from this to that. So I can talk about the 2 Hom from the matrix DST to EST. This is the set of matrices, so T by S matrices of bijections from DTS to ETS. Yeah, these should have been DTS and ETS. Okay, TS, 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 TS. For example, here's another. So this was in what? This was in Hom of 1, 2 to 6. Here's another matrix in Hom of 1, 2 to 6. Alpha, beta, gamma, delta, epsilon. Theta, eta, iota, rho. And here's a 2 homomorphism from this to that. This goes to there, and 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 this goes to there. So that's one of many 2 homomorphisms. So this language has no actual meaning, but I've sort of categorified numbers. I've categorified rather abelian groups. So in the sense that I have now an additional level of structure that I didn't have before. Before I could talk about an abelian group. Okay, here I'm thinking about abelian groups with basis, so it was a finite set was the basis, and a map between 2 abelian groups. Here I can talk about objects and morphisms. They're these matrices, but then there are morphisms between the morphisms. It's a matrix of bijections. Okay. This forms a 2 category. A 2 category. There's a forgetful map from this 2 category just to abelian groups. So B maps to abelian groups by, okay, the objects were the same, right? If my abelian groups are abelian groups with basis, that's these things. So the objects were the same. And now if I have a matrix ASATS, just maps to the number of elements in each entry. Okay, so if I had, for instance, my matrix there, A, B, D, empty set, sorry, not empty set, it was C, empty set, E, F, this maps to the matrix 2, 1, 1, 0, 0, 2. Piece of cake. And I mean, matrix multiplication goes to matrix multiplication. This is a functor. So I'm going to lift, so we'll lift the Khovanov cube. So we had this cube-shaped category, 2 to the n. Again, 2 to the, well, I'll give some more notation in a sec. And that was mapping to abelian groups. That's what the Khovanov cube was doing, CKH basically. I'm going to lift it, this I need to define, to a map to the Burnside category so that this triangle commutes. The Burnside category comes with a nice map to spectra. I'm going to explain that. I'm going to explain it wrong today, and I'm going to explain it right in like 3, 4, whatever number of weeks we eventually get there, because there's some interruptions, but like in 2 lectures. But this is well known. But I mean, it wasn't well known to me, so there's a non-trivial chance it's also not well known to you. So I will explain it. So the next thing I'm going to actually do today, we're doing so well. The next thing I'm actually going to do is I'm going to explain this arrow. And before I do that, I'm going to explain, again, mostly explain this arrow. Before I do that, I'm going to explain, what is the data I need to specify a map like this. What's the data I need to specify a map like this? I need to specify an abelian group for each vertex, free abelian group. In other words, a set, and a group homomorphism for each edge. And then like 2 to the n has lots of maps in it, right? Here's 2 to the 3. But like, that's not actually 2 to the 3. There's like another arrow that goes that way and one that goes that way. And if my map's going in circles, this should have gone that way. And there's a long arrow that goes all the way to the back. But any of like this arrow is the composition of those two. So once I told you what map associated there and there, I've told you the whole thing. So I'm going to tell you the analog of that for maps to B. It's slightly more complicated because B was a 2 category. And then I'm going to tell you how you actually do it in the Khovanov case. What you should be listening for, what you should be listening for is what's new? Am I just recapitulating the old definition with some like ridiculously complicated, unnecessary language, or where is the new information? And so that's going to be like, keep watching, where is something new? Am I completely wasting your time? Well, in the grand scheme of things, yes. But in terms of mathematics, no. For instance, there are knots which have isomorphic Khovanov homology, but not stably homotopy equivalent Khovanov spectra. So this does have new information. So there's got to be some new input somewhere. Okay, so I'm not completely wasting your time in some extremely generous sense. Okay. So to specify a map from the cube to this Burnside category, I need to specify its value on each vertex. So I need to specify, so choose a set, finite set, f of v, for each vertex v. And the set you're supposed to have in mind is the set of generators of the Khovanov complex over that vertex. So think the set of generators of the Khovanov complex over V. So I'm even getting close to here. So like here's not our familiar knot. This is a different, well, link. Here's its cube of resolutions. And here's the set that I'm going to specify over this vertex. Yeah? Yeah, it's going to depend on the knot diagram. That's right. Just like that's a great question. Yeah, just like the Khovanov cube depends on it. So I'm going to give you for each knot diagram. This is a great question. For each knot diagram, I need to find you an arrow like this. This is not dependent on the knot diagram. This arrow is just a standard construction that I'm going to give you for a mass from beta spectrum. But so this is where the knot input is. That's a great question. A little bit more terminology, maybe. So, well, no, we could do without. I need to give you a matrix of sets. So morphism in B for each edge V to U in 2 to the n. That is, for each of the edges I've drawn here, for example, I need to give you a matrix of sets. I'm going to draw that sort of schematic again. Let's stick with squares. So like, well, here's like the vertex here, the 0, 0 vertex, the 1, 0 vertex, the 0, 1 vertex, and the 1, 1 vertex. Here's the whole category. Here are all the non-identity morphisms in this category. Now, if I've given you the morphism for each edge, I've told you the map for this diagonal, but I've told you it twice. Okay, so I gave you, here I gave you a map f of 1, 1 to 1, 0, and here I gave you a map f of 1, 0 to 0, 0. So I could define this to just be f of 1, 0 to 0, 0 composed with f of 1, 1 to 1, 0. But I could equally well have defined it to be going along this edge and that edge. So, or I could define it to be f of 1, 1, sorry, of 0, 1 to 0, 0 composed with f of 1, 1 to 0, 1. So, well, I mean, I better not have two completely unrelated definitions for this arrow. So I need a two-morphism that is a bijection of sets in B for each square. That is, in this case, I need a bijection between that matrix of sets and that matrix of sets. Bijection, I mean entry Y bijections between these things. OK. And 3, these should satisfy a condition around every 3 cube. There are no 3 cubes here. This is 2-dimensional. So there's no extra condition, compatibility condition. But as soon as I go 1 dimension up, there's some compatibility condition here. And that's on the homework exercise. There's sort of only one thing you could possibly write down there. And so the exercise is to write down the only thing you possibly could. It's in, I mean, I'll stick a reference in the web page also. Where is the new information potentially beyond Khovanov homology? It's here. In Khovanov homology, either this is a matrix of integers. So either this matrix product and that matrix product are equal, or they are not equal. In this world, they can be equal in lots of ways, because being equal means there's a bijection of sets, and there can be lots of bijections of sets, as long as sets have more than one element in some entry. Okay, so new information is here, and the new information has to satisfy a compatibility condition there. Questions? I owe you. I will tell you. I haven't told you. Yeah, the question is what is it in Khovanov homology? So that's next. A prescient question. So great. Let's go to use here. So this is my favorite. Not again. I didn't draw all the rest. I mean, this is like the 70,000th time I'm drawing the cube of resolutions, but like its cube of resolutions was this. Okay. So these are the sets f of v. So like this is the set f of 1, 1. And this is the set f of 0, 1, etc. Here, I need to give you a 2 by 4 matrix of sets. Okay, that's the first thing I owe you, is a 2 by 4 matrix of sets. The 2 by 4 matrix of abelian groups, let's write that. 1 times 1 goes to 1. 1 times x goes to x. X times 1 goes to x. And x times x goes to 0. So this is the matrix that shows up in the Khovanov differential, where I've ordered the basis in this order. Is that OK? Did I do that right? I claim this is the old-fashioned Khovanov differential. This is just saying 1 times 1 is 1. 1 times x is x. So this 0 1s and 1x. It's plausibly OK. You guys don't have to suffer. Just any questions? Now you can't ask questions. Awesome. Good job, me. I've talked myself into a corner. We're going to keep going. There is no new information in what I'm assigning here. So I'm going to assign f of v to u, where this is an edge, is the matrix of sets with one element if the entry there is 1, and 0 elements, like the empty set, if the entry there is 0. So along this edge, my matrix is set of star, empty set, empty set, empty set, empty set, star, star, empty set. Which one element set? It doesn't matter. All one element sets are the same, in the sense that there's a unique bijection between any two one element sets. So it doesn't matter what one element set I choose. So just choose your grandmother or whatever, your favorite one element set, and put it everywhere. Okay? This is no new information. Right? Nothing new has happened, except I wrote stars instead of ones. Now you're wondering, wait, what if there were 2? Like, what if I had entry 2 in this matrix, or 7, or -3? And the answer is you never do. In the Khovanov complex, the entries are always 0 or 1. So that doesn't happen, not a thing. Similarly, this matrix is 1 goes to no copies of 1 tensor 1, 1 copy of 1 tensor x, 1 copy of x tensor 1, and no copies of x tensor x, and x goes to empty set, empty set, empty set, star. Okay. Now, if you multiply two of these matrices, such as these. I can multiply them. I have to use my fingers this way, but let's see. I got empty set. Oh, let's do that. So for example, here, yuck. It's going to be a 4 by 4 matrix. I'm totally capable of this. Empty set. It's not going to be a 4 by 4 matrix. Good try, Robert. It's going to be should be a 4 by 4 matrix. I'm multiplying wrong. Try this way. Empty set, empty set, empty set. OK, I'm very good. Empty set. Wow, this is exciting. Empty set, empty set, empty set. OK, maybe we're not learning as much as I'd sort of hoped. Empty set, empty set, empty set, empty set, empty set, star, star, empty set. Wasn't that interesting? OK. I mean, if you go around the square, 1 tensor 1 goes to x tensor x, and that's the only. What have I screwed up? Well, I screwed something up somewhere. Let's ignore the fact that I screwed up the computation somewhere. It doesn't matter. All of the entries here have 0 or 1 elements. All the entries here are going to have 0 or 1 elements also. So there's a canonical bijection between entries. No new information so far. So if the entry has 0 or 1 element, there's a unique bijection. Let's just ponder that for a second, because I'm losing everybody. If the entry going this way has 0 elements, the entry this way also has 0 elements, because the number of elements was gotten by multiplying the matrices here, and we knew that it commuted at the level of abelian groups. So either they're both 0 or they're both 1. I mean, the number of entries has to be the same, because it's given by after we apply the forgetful map. However, sometimes there are 2 entries. So the interesting new data is if there are 2 entries. Eek. And now I will try to get this computation right, because this is one where we do get 2 entries. So 1 splits to 1 tensor x plus x tensor 1. Let's just give these names so I don't lose track. A, B, empty set. X splits to x tensor x. C. Is OK for this entry? This is the split map. You guys are looking a little more lost than I expected, which is fine. I'll keep doing it, and maybe it'll become clear in a sec. Here, 1 tensor 1 goes to 1, so that's like, I don't know, D, empty set E, empty set F, empty set, empty set.
So above you said it didn't matter what the element was because there was a canonical bijection, but here you're picking different elements.
Yeah, so why am I doing that? I want to just have names in a second, so that when I do the bijection, you can see this goes to that, as opposed to this star times star goes to that star times star, and it's invisible. So this is just for convenience in a sec. That's a great question. Let's label, so there they are. I'm stealing the chalk. Let's label this. So this diagonal arrow, if I multiply these matrices, it's going to be a 2 by 2 matrix. I'm capable. Ooh, they're even written in the right order. Empty set. Empty set. Ooh, how very exciting. EA, FB. EA, FB. And then empty set. So it's a matrix with one off-diagonal entry that's non-zero, non-empty, and it has two elements. I'm going to keep torturing you. There's a symmetry. So this diagram looks exactly the same on the other two edges. Empty set, let's give it a new name. D, E, F, G, H, empty set, and empty set, empty set, empty set, K. And here, L, empty set, empty set, empty set, and empty set, M, N, empty set. And now when I multiply them, I instead get the matrix. I'm so good at multiplying matrices. Empty set, G, MG, NH. MG, NH, empty set. So the new data is I need a bijection here. Okay. Ooh, running a little behind. Let's and so I actually wrote out how to do that in the homework, and maybe I'll come back to it in 2 lectures. I'm going to say it really briefly. If we look at that diagram, let's take the 1-1 resolution. There's the 1-1 resolution. And let's remember where there were crossings. There was a crossing there, and there was a crossing there. If I walk along the edge and I turn right, walk along the crossing, the orange edge, and turn right, I can get to this point or this segment or that segment. Choose either one of them. Okay? Maybe this one. That was just choose at random one of them. It makes no difference what I'm about to do. Now, look at the label of my preferred segment at this vertex and at that vertex, and use that to match up to choose this bijection. So use label at here to match up the bijection, or match up the matrices. That was too fast for you to follow, though I think it's enough that if you sat down for half an hour and worked through that example, you'll figure out what I meant. Also, there's some hints on there's some explanation again in the homework. What should you take away from it? There wasn't much new information. There was one case where we had this bijection, and we call this the ladybug matching. If you draw that differently, it looks like a ladybug. Good job, us. But it uses something about the way these circles sit in the plane, which actually nothing else in the Khovanov complex is used. So this uses something about the way things were embedded that's not shown up anywhere else in the instructions. So there's not much new information, but it's a new kind of information. OK. And now I want to tell you how you go to a diagram of spaces so I don't completely run out of, not get anywhere. And the iterated mapping cone, well, it's also in the homework, but I'll say next time or the time after. So here's the lie about how you go from this category to spectra. In spectra, that is up to stable homotopy equivalence, so up to stable homotopy equivalence, said correctly, which is a little complicated actually, x cross y is the same as x wedge y. So the product is the same as the coproduct. That's just like in abelian groups. In abelian groups, the product and the direct sum are the same thing, finitely generated abelian groups. Okay. So now, so I'm going to pretend these are exactly the same thing. So I'm going to take, let's take that example, actually. Let's take that example. So that example is going to become sphere, wedge, sphere, wedge, sphere, wedge, sphere, sphere, wedge, sphere, sphere, wedge, sphere, wedge, sphere, wedge, sphere, sphere, wedge, sphere. The sphere has a, S just means sphere. So S, just think of it as like Sn for some big n. Though actually n doesn't matter at all for what I'm about to say, except bigger than 0. The sphere has a pinch map. So it has a map to sphere, wedge, sphere, which is just you had a sphere, and you pinch it. Okay, so this is the pinch. Just quotient the equator. That gives you some sort of co-multiplication on the sphere, which is then when you take hom from the sphere to your space, that gives you the multiplication on pi n. And so the operation on the homotopy groups comes from that. Addition to homotopy groups comes from that. So how does this map not work? For an object T in the Burnside category, I get the wedge sum over T and T of the sphere. And now, given a ut from, I have like 1 minute, from T to U, I should be getting a map from the wedge sum over T and T of the sphere to the wedge sum over U and U of the sphere. All right, that's what I should get. This is the same as the product over U and U of the sphere. Now, if I wanted to find a map from a sum, it's enough to define it on one summand. Right? That's the universal property of coproducts. And if I want to find a map to a product, it's enough to define the map to a single factor. So by universal property of product and coproduct, I might as well assume that U and T both have one element. So I'm just defining a map from a sphere to a sphere. So I've just got a map from S to S, want. And this is the map, is the map with degree the number of elements in the correspondence in the matrix. I mean, if I've just got one set, my matrix just has one entry. It's a set, and you count the number of elements in that set. So I will tell you where the lie is. The lie is the V. And actually, there's a homework problem to show that actually no way of doing what I just said works. But it's approximately correct. And I'll fix what the word V is and give you this map. And also something about mapping cones next time or the time after, depending on my mood. OK, I'll stop there. Thanks for listening.